A warm welcome to everyone here today, and we're looking forward to Johan's Reader's Digest selection. But let me first introduce Johan first. He's currently an associate professor at the University of Pretoria in the Department of Statistics. He's also a junior focus coordinator for the Statistical Theory and Applied Statistics focus area of the CoE-MaSS at the University of Witwatersrand. He regularly publishes in accredited peer-reviewed journals, review manuscripts in international journals, and is also an integrated researcher. He's also an ASLP Fellow of Future Africa, and in 2016, he was identified as one of the top 200 South Africans under the age of 35 by the Mail and Guardian newspaper. So please, a warm welcome, Johan, and I'm looking really forward to you. Thank you.
Thank you so much to the CoE for the invitation. I'm very glad that we have an audience online because we barely have space in person. There's just a clamoring of feet to get into the venue, and it is my privilege to share some ideas with you today. As Prof. Bakker introduced me, my name is Johan. I am at the Department of Statistics, University of Pretoria. And when I thought about what I'd like to share, also given the time constraints, I thought maybe I can give some ideas of where exactly do my focus area, or at least my focus interests, emanate from. And I thought about packaging it like a story, and that's why I decided to call it the Reader's Digest selection of recent contemporary results, which emanates from distribution theory. And distribution theory being the core emanating entity of much of where statistical research comes from. So we have to think about the Poisson distribution and departures from that when we are looking at data that might be integer valued. And so this was where one of our stories started, from a usual autoregressive model, but immediately the counting changes, and hence the error structure also changes. When we look at an example of data that is discrete, we see that when we do connect the points, it might look continuous. However, these points in the upper left-hand corner are all discrete values observed over time. And then we have the autocorrelation function, the partial autocorrelation function for this downloads data set that comes from Weiss in 2007. We immediately see from our usual autoregressive theory that an autoregressive model of type 1 seems like it might be a good model fit. So, inspired by Weiss, we now have to amend our autoregressive structure slightly because we're not adding continuous errors anymore. We're probably going to be adding a discrete something to that. So we have an integer autoregressive model, which is defined by P thin xt minus 1 plus some error term. P is between 0 and 1, and the innovations are independent and identically distributed with some discrete counting range. And that's exactly where the twist in the tail comes in. We have to now think of not only a symmetric normality assumption as in the past, but we also have to think of something that is discrete and positive. This circle denotes the binomial thinning operator, which is how the integer autoregressive models are defined in order to adhere to the requirements of the model being counts. And it is defined as a finite sum of Bernoulli random variables, where then, of course, our epsilon t must follow some stochastic discrete distribution. And a variety of authors have shown that the performance of this ENR1 model, by assuming the usual Poisson as an error structure, has been done. Also, other count models, negative binomials, also a Poisson-Lindley type of error structure. But in these cases, the challenge remains in the sense that equidispersion is a theoretical restriction on empirical data, which might not be the actual case. So, where did our dream come from? We thought, let us consider the Lindley. distribution. The Lindley distribution has a two-mixture component between an exponential model and a non-central gamma model. In the usual Lindley case, it's not a non-central gamma model, it's a usual gamma. In this case, we thought, let's add in this non-central component. Non-central component being a parameter lambda. And there's a reason why we are looking at the non-central component of the gamma distribution here. We found a closed form expression, which is in equation 2 for that. And then subsequently assuming this Lindley model as the assumed distribution in a compound setting for the rate parameter of the Poisson distribution. In this way, we will eventually obtain a discrete distribution, Px, and this Px might be of interest to determine how the error structures of this Yt might behave. Now, the inspiration here comes from the fact that over-dispersion or under-dispersion or departures from equidispersion is a challenge. And by introducing a non-centrality component, gives you or me or whoever uses it a direct insight and leverage over what the expected value of the model would do. Also, as part of the numerator of the dispersion index, meaning we might have additional insight built here in order to address possible departures from dispersion. We have this wonderful closed form expression as a new discrete contender that can be considered within this inner environment. It's closed form, there's little convergence issues, and we also found that the cumulative distribution function, the probability generating function, moment generating function, all of the other usual type of characterizations of the distributions, which is a tractable utilization of this lambda parameter. And this lambda parameter is our direct focus here. When we just look at what this Poisson non-central Lindley model would look like, we can see that when we increase lambda, we do increase the mean of the distribution, which means that if this is the theoretical behavior of our error structure, we can immediately potentially capture departures from the equidispersion index. Just as an illustration, we can see that if lambda does increase, the mean increases of the entire model. The variance increases, but our focus here will rely and remain at the dispersion index. And we can see that potential departures, especially in the case of over-dispersion, can be captured by considering this lambda, lambda being inherited into this model from the non-central gamma that we consider instead of the usual gamma. So it's a systematic construction to include a parameter with an interpretable field to address a specific challenge that is evident, usually encountered within our environments, that of equidispersion in the case of the Poisson. We can, of course, now go and fit our model, and we fit it to different other models as well, to show its competitive nature, or just to show its behavior, or just to show its performance. There's a data set of daily number of downloads of a certain software, and now over time, we would like to fit not only the usual Poisson as in the first case, we also fit the negative binomial, we fit Bell innovations, we fit a 3-parameter Lindley, and we fit our own Poisson non-central Lindley. We have to kind of gauge, how well does this fit? Does this fit at all? Was this a good idea? I don't know. So let's see from a practical perspective whether we do gain some insight when it comes to this newly developed model. In this case, we can, of course, use varying amounts, varying different measures of goodness of fit. In the case, the AIC, in this case, shows us that the lowest AIC is in bold. I'm not sure if you can see the bold. It's the 1082 from the negative binomial model, which means that the negative binomial model fits better. But just out of interest, when we do look at the negative log likelihood, we do see that our negative log likelihood is slightly won over by the Poisson non-central model, 537.6. I'm not trying to convince you that this model is the best model in the world. I'll speak about that in a moment. But it does show that this model seems like a reasonable inclusion as a contender in these type of scenarios. Out of interest, we see also in the first line when assuming a Poisson distribution, the mean and the variance is the same. But the observed mean and the observed variance for the data set in the second line at the top of the slide, 2.401 and a variance of 7.534, you immediately can see that there's a departure from a variance that is observably much larger than what a Poisson model would give. So even in that case, we do see that the negative binomial variance is slightly higher. The Poisson non-central limiting one is still a good contender, bearing in mind that there's few more parameters to estimate as well, which of course also comes into play thinking about a parsimonious type of model. However, did it fit the data the best? Absolutely not. Well, reasonably so. But I think it is super, super important to keep in mind that there is no one ring to rule them all. It depends on the data. For a different type of data set, it might have turned out differently. So I'm trying to play open cards with you here. I'm not trying to show you Johan and team thought of a model, and this model seems like a brilliant idea. I think the model does seem like a brilliant idea. However, it must be kept in mind that it's a contender, not one ring to rule them. The systematic construction of this model gives insight and leverage into the challenge of equidispersion when we get to integer valued time series. Because of this lambda, which has an intuitive non-central, meaning departures from the mean, that is inherited into a Lindley model and into a Poisson non-central Lindley model, which is inherited by the in-out process where we want to apply it. So there's a few wins here, not only a general non-central type of Lindley model, but also a general previously unconsidered counting model. And that counting model, the Poisson non-central Lindley, illustrated within an in-out environment. This work has been published, entitled A Non-Central Lindley Construction, illustrated in an in-out one environment. This is our first story. Story number 2. Bits of mixtures, shapes, and sizes. Now, we're pivoting away from the time series environment. We're pivoting away from a univariate environment. And we are charging into the multivariate sphere. In this case, multivariate data, especially the type of data that is modeled on the unit simplex, are often modeled by the Dirichlet distribution. Unit simplex, it usually means that we're working with data that is constrained onto the bottom triangle between 0 and 1, meaning proportion data and data that should sum up to 1. The one drawback of the Dirichlet distribution is that theoretically, data on the unit simplex must be negatively correlated, theoretically. In practice, that is often the case, but in practice, it is also sometimes not the case. But the other win of the Dirichlet distribution is that you're working with a density that is relatively simple to implement. And then in a Bayes setting, when you are working with k distinct categories, the Dirichlet is a convenient choice as conjugate prior for the multinomial model. A k number of categories in the multinomial setting will result in a k-variate Dirichlet being incorporated. So multivariate discrete random variable x has this multinomial distribution as a generalization of the binomial case. Binomial where we have two outcomes, success or not success, true or false. But in the multinomial case, it's just more than that. Not only 2, maybe 3, maybe 4, maybe 5, your choice up to k. And then throughout all of this, we started with the Dirichlet idea. It works nicely with the multinomial. And then when we want to estimate parameters in the Bayesian sense, oftentimes entropy is something that is of particular interest. Entropy as giving us a sense of how much information is actually contained in the model. Either we want to estimate entropy itself, or we can use it as an additional tool to estimate parameters in a more accurate and a reliable way. So let's talk about this entropy for a moment. The most popular form of entropy is that Claude Shannon introduced in the 40s, which is the sum, finite sum of negative pi times the logarithm of p. And various generalized versions of this entropy exist, which relies on the power sum. This power sum also still retains close connection to this pi being the probability that an event will be observed within category K. We have this finite sum, and immediately if we compare h of p and f of p, we see that they are very similar in the sense that they are both finite sums, and they both use this expression pi, which is the probability. And in a Bayesian sense, if you assume squared error loss, for example, we can just take the estimates of this entropy as the expected value of these functions, either Shannon or the power sum. The convenient result of this is in equation 5, where we can estimate the power sum by using the expected value of the probability up to some level alpha. For example, if you want to look at Thales entropy, which is a usual departure or generalized version of Shannon, we immediately can write an estimate of Thales entropy in terms of this estimate of the power sum. Something that does not work as convenient when you're looking at Shannon, because that logarithm in the expression for Shannon is particularly challenging. So this entropy idea spans k number of categories, and there are k number of PIs. So when we are looking at k number of categories, each with some resultant probability pi that might follow some a priori defined distribution, let's say the Dirichlet, the estimation of entropy becomes quite tricky if it's Shannon. But our dream here is to show or to utilize this power sum as a generalized form, which is slightly more convenient to implement. Our plot line for this story goes: we consider the Dirichlet as a prior for the multinomial model. I can hear some of you thinking, hang on, Johan, doesn't the Dirichlet multinomial model exist? Absolutely, it does. So we want to use that almost as a benchmark. By using the Dirichlet as a prior for the multinomial model has been done for many years. Tiny drawback of the negative correlation. If you want, or if your data would exhibit positive correlation, the Dirichlet might give you a drawback. And then we want to incorporate this idea of entropy in a sense to see what happens. We are completing our quest to determine a posterior distribution. We want to look at the moments of these multivariate distributions, and we want to find the resulting estimator for the power sum. Because if we have an estimator for the power sum, we have an estimator for a generalized form of entropy. And we want to see how we can utilize this in a data fitting context for optimal estimation. So if the Dirichlet has this negative correlation restriction, what can we do to go and see what happens with it otherwise? What changes can we make? So just as a recap, our Dirichlet is given by equation number 6, where our unit simplex is this sum of probabilities must be less than 1, all the probabilities must be greater than 1, and the last category must be the remaining normalizing probability. And the very nice thing in this case as well is that we can find the expression for the joint product moment for this model in equation 7. When I say tractable and when I say convenient, I mean it's a closed form because it's a finite sum in terms of gamma functions. Gamma functions being implementable in software of your choice. Okay, but this Dirichlet is the challenge. So let's look at something else. Let's call it Dirichlet with a tau twist. We're calling this the flexible Dirichlet. This flexible Dirichlet, we're going to purposefully build it as a mixture model. Myths of mixture in the story manifesting here now. So in this case, we are introducing an additional set of parameters granted in terms of weights, which are the betas, and this single tau. Basically, what this tau is doing is we're putting a tau jump, tau size, tau magnitude jump on each corresponding pi I. Pi I being, of course, our power of the probabilities in the usual function in equation 6. And when we add this tau jump to each of our pi i's, we get, number one, of course, a mixture model because we define it as such. But also we find a mixture model in equation with density given in equation 8, which is still in closed form and retains many of the observations, not observations, many of the characteristics as the usual Dirichlet does. So our interest here would be to check, okay, this equation 8, would it exhibit positive correlation? In this case, just as a side note, this number 8 includes the Dirichlet as a special case, but that almost follows immediately. And then in equation 9, we can find our joint product moments. Why joint product moments? Because the joint product moments can be used immediately in terms of finding or observing the correlation. Again, it's closed form, which is a very nice observation to make. Finite sums in terms of standard mathematical functions, such as the gamma function. Another thing to keep in mind here is, of course, that the mixture of these type of Dirichlet would inevitably potentially result in multimodality when you look at your quote unquote prior that you're actually considering in the Bayesian sense here. So that is something to keep in mind for prior data that might be behaving in a multimodal fashion. The mixture of the Dirichlet, in this case, flexible Dirichlet, can account for that in some way. But our question also remains, correlation, what if data is positively correlated? Because that is the drawback of the usual Dirichlet. Well, I'm sorry to break it to you, but this mixture of Dirichlet does not have any positive correlation, unfortunately. So that was quite a bummer, if I'm going to be honest. But then we thought, okay, I'm quite a stubborn person. So let's put another mixture on and see what happens. So a flexible Dirichlet with a further tau twist, and we call this the double flexible Dirichlet. This double flexible Dirichlet is a two finite sum mixture, again, in a relatively closed form. This closed form in equation 11 shows us immediately that there are, of course, a little bit more complex arguments that is entering the game here. But it's still a mixture, and I say mixture and I put brackets, mixture again, because it's kind of a mixture of a mixture. So multimodality on the simplex can still be quite easily captured with this, or at least that's what we feel. And then now the question comes in, correlation, because that's what we're chasing. We want to observe a departure from negative correlation in the case on the simplex. And just as an illustration, this is the type of contours that the double flexible Dirichlet offers us. It shows us immediately that there can be a variety of modal points observed, but it doesn't necessarily have to be multimodal. It depends on the choices of parameters, or in effect, the behavior of your data a priori, or your parameters a priori, and determining then the flexibility that the model might need to encounter for this. But of course, then also we need product moments. Product moments so that we can go back into Pearson correlation to just have an insight into how this might behave. By doing this, of course, mixture on a mixture on a mixture until you are blue in the face. But in this case, we see that our product moment, although it is slightly more complicated, is still finite and in terms of well-known mathematical functions. So immediately now we can say, okay, well, we don't know anymore. Let's take a guess, and we are going to incorporate this or observe whether our double flexible Dirichlet offers some positive correlation. And in fact, it does for different parameter values, we illustrate it here with a heat map. We see here for the different parameter combinations that we try, the values that go up to the yellowish area in the bottom left corner of both of the heat maps. You can see that there's quite a high level of correlation that can be observed, up to 0.7. This is a major consideration in the Dirichlet or simplex type of modeling. I'm not saying this is a major breakthrough. I'm saying this is a major plus when we do want to view stuff with a Dirichlet tool in order to model potentially positive correlation on the unit simplex. The double flexible Dirichlet does not only have positive correlation, but it also has positive correlation. And this consideration is meaningful. Of course, we saw that our power sum, going back to entropy, can be written as this finite moment sum. So that is also why, not only for the correlation that we wanted to find the product moments, but we already have the expression necessary for the expected value of pi to the power alpha, because we already have the complete joint product moments. So deriving these complete product moments is not only a routine exercise. I think many people might feel deriving moments and deriving a moment generating function, and the characterizations of a distribution can be quite a routine textbook exercise. That's sometimes, unfortunately, how I think we approach it in the undergraduate courses. But in this case, it was absolutely necessary for us to see that there's a breakaway from negative correlation, and we can access a generalized entropy form by using these product moments. In this case, we use our estimates of our entropy, as well as the estimation of the parameters of the posteriors that we derive to a certain type of economic data. There are three graphs that you see here. And in this case, the three graphs are using different slight variations of generalized entropy. On the left, we have Thales, as I illustrated earlier. In the middle, we have Matai, which is another generalized entropy. And on the right, we have the Abe entropy as well. Of course, you can look here and see, Johan, are they that different? Well, in this case, we can see that the calculated entropy from each of these are different. Entropy of Thales 1.36, Matai 0.75, and the Abe entropy is 0.84. And immediately now, we can also gain insight when we look at the behavior of, or at least how much information we'd like to think is contained within the system. Of course, this is drawn for the Dirichlet prior. Unimodal, potential negative correlation. And now I'm showing just results to you for the flexible Dirichlet prior. And immediately by considering the flexible Dirichlet prior, we can see a sense of clustering that could be occurring in the background. Warrants further investigation, depending on where your data comes from. But immediately we can see maybe there is some kind of inherent clustering because of the different modes that are occurring, because we are considering a mixture type of model. So that's our question, additional follow-up question to be followed up here. Does the flexible Dirichlet and the double flexible Dirichlet reveal specific information regarding potential modal points for the underlying model that we should be discussing further? So our resolution to this story, did it fit the best? Well, depends. Again, there is no one ring to rule them all. It depends on the data. However, the systematic construction of these mixtures gives insight and leverage into the challenge of, number one, data that occurs on the unit simplex, such as ratios, not ratios, proportions, and multivariate consideration for positive correlation on the simplex. And number three, base type of estimation for entropy when we're working with a finite number of distinct classes. This work has been published. It has not been published, it's been accepted, but hopefully it will be appearing within the next week or two. It's called Thales and other generalized entropy forms subject to the Dirichlet mixture branch. And now we get to our last story for the day, when we talk about something called directional statistics. And because it works with data that often occurs on a circle, I decided to call this circles in the forest. Forest? Why? Are you just copying the Leen-Matthee, Johan, the famous Afrikaans author? Not quite, because when we think of a forest, there's usually some type of animals inside the forest, and our inspiration for this story came from modeling data of animal movement. In this case, we look specifically at the data set of caribou that is observed in Canada over a time period, I think it was 2015 to 2016. Now, this is immediately quite a broad range of thoughts that has to go into this, because an animal inherently has to be classified into being in a state of some kind. Are they resting? Are they walking? Are they eating? Are they sleeping? So immediately our type of model and where this data comes from can get quite tricky and quite overwhelming. And I'll speak more about that in a moment. Just as a complete interesting side note, so when we started this study, for such a long time, I was convinced. I didn't tell anyone, I accidentally discovered it myself. Because we were working with the caribou data and we were modeling all of this. And I was convinced that a caribou is a bird. I thought like, oh, this is ornithology type of arguments. And then one day I had a discussion with a friend and I said, no, it's this bird type of data that we're looking at, caribou. And then they said, but is that not a large mammal? So that was a different type of enlightening moment for me as part of this study, to actually learn what a caribou is. Directional data, because we're working on the circle, has something to do with data that is observed on the circle. This is a departure from our usual point of view or our usual point of comfort, because it's not data that is just conveniently plotted on in the real space, or at least in the linear space on XY axis. So immediately we have to start thinking about, okay, an animal can travel a distance, so far, so far, so far, but an animal also turns in a certain direction when they might be going here to eat something and going here to run away from a lion and going here when they want to have a drink of water. So the type of data that we are collecting is not only real, for example, the distances. It can also be directional. So immediately our point of departure or focus when we are going to look at this type of models has to include data that is distributed or can be modeled on the circle. Directional. So various stats techniques and animal movement models are required to model this animal movement. There's so many things to keep in mind. And the major challenge remains in the validation of a statistical approach, since the true and exact behaviors of animals are not always known. You can contextualize this as the type of inference and the type of discussion that would happen in the Kruger National Park for Nature Conservancy, to realize and be able to have an idea of when you expect animals to be where. And that depends on not only how far they travel, but also in which direction they travel. And within discrete time, we describe or characterize displacement of an animal by direction and distance between two consecutive points in a necessarily circular linear process. And we model the movement within this two-dimensional environment. And two primary factors which characterizes this movement is the direction, as we've mentioned, the angle between two successive time steps in which they travel, as well as the distance traveled by the animal between two consecutive time steps. So popular choices. What is being done in the literature? For the directional model, researchers often consider the von Mises distribution on the circle. And for distances, they sometimes use the gamma or the Bible. So now we have to think, and where this inspiration comes from. Okay, angular data on this circle as the rose plot, as I showed earlier, might be multimodal. It depends on the data. We've said that a few times today. It depends on the data. It might have different or varying levels of skewness. So immediately we have to think, what type of departures is warranted in a practical way from our usual theoretically considered models? The same goes for the real or the linear case, considering distance. Gamma and Weibull, what type of restrictions may they have? What are the price of those restrictions? What can we meaningfully do to consider these or departures from them? So, within angular setting, especially here, the direction of animals, directional models needs to be employed, but like I said, data can be skewed, multimodal. Therefore, the usual assumptions that is embedded and what's the word I'm looking for, imposed by the usual von Mises might not be practically viable. Maybe they will be, maybe they won't. And then within real settings, specifically here, the distance traveled by animals, real positive models may also depart from standard univariate models due to increased or different skewness and orthosis or other practical observations. So the plot thickens. We thought, okay, so a meaningful, potentially practical consideration would be the consideration of the sign-skewed von Mises distribution for direction. It's a generalized version of the von Mises distribution, which can account for multimodality and also for skewness. Out of interest, equation 13, see that YT is not distributed on a linear scale. It is distributed between minus pi and pi, or the range is between minus pi and pi on the circle. So immediately we are taking a step back and have to, at least I have to reevaluate how I thought about the way the data behaves, not only on a linear XY axis, but also on the circle. And then for distance, we thought, well, the gamma works, or at least the gamma is being used, and the Weibull works, or at least the Weibull is being used. So let's consider a two mixture component of those two to see if there is a play-off and a trade-off when we are considering the gamma and the Weibull, but combined. In this case, considering the two mixture component of the generalized gamma and the Weibull distribution results in a power Lindley model. Neither of these two models have been explored in the animal context environment yet. And this was not the only reason. The main reason being inspiration drawn from potential anticipated practical departures and how we can seemingly account for that in a meaningful and impactful theoretical way. That's why I asked, do these make sense? Well, they do make sense because they do still contain the usual models as special cases. And the departures that we are inducing here in terms of the multimodality and the skewness makes sense practically, probably. Oh, and we added the Gumbel distribution as well for an additional reference and benchmarking. So we have this data set YT, DT, and I see we are, is it okay? Okay. We have this data set for a certain number of time steps, and we are going to try and explain the behavior of YT and DT in terms of the explanatory angular and the explanatory real variables in a circular linear regression context. We have this obvious, not obvious, my apologies, I should not say that, this hidden, almost criminal underlying stochastic process that necessarily accompanies our analysis. I mentioned earlier, animals can be sleeping, they can be walking, they can be eating, they can be drinking, they can be resting. So there's a large number of states that animals can be in. And that necessarily accompanies the argument of whether they are turning. Are they turning? No, they are sleeping. Or are they walking? No, they're not walking, they are eating, or something to that effect. So the hidden process is also incorporated via a hidden Markov model. And our joint PDF for all of our data is then given by equation 14. And this type of model, we estimate the parameters using an EM algorithm. And we apply this to the movement of forest caribou, where locations were measured every 4 hours during the 2006-2007 period. And we had the 4 variables as discussed earlier, and we fit specifically only a 2-state hidden Markov model. Of course, we can add more than 2 states, but in this case, we consider traveling and encamped, whether they are stationary or whether they are moving, to observe what happens if we do go and tinker with the theoretical underpinnings, namely, what model are we using for the angular variable? What models are we using for the distance variables? And so there's a large table. What I basically want to point out to you is, unfortunately for us, the Gumbel distribution, which I just included as a benchmark, outperformed everything else. This was strange to me. I'm talking about the distance models in particular. This was quite strange because usually you can think that the gamma and the variable, or at least a combination of that, would also work better. And I also mentioned earlier, I'm a very stubborn type of person. So I thought, what can we go and observe in this case? Or what can we go and do? Because I had to know for myself whether the inclusion of the powered Lindley, being practically motivated as a 2-component mixture of the usual considered models, might be meaningful or not. And even when we look at the distance fits here, we see the distance fits are quite terrible, or not that terrible, but we see here, for example, that the gamma model fits well. The powered Lindley model, at least in the tail area, fits well, but in general was not a great fit. So I call this the resolution of our story, and I say resolution-ish because I was quite stubborn. So I thought, okay, if we go take our forest caribou data and we bootstrap from it one sample of the same size, we bootstrap it, fit the model again, see what happens, and we bootstrap it again, fit the model again, and we do that 300 times. Then we will have 300 parameter estimates of each. We will have 300 AIC values or log likelihood values. And I thought to myself, if there is one instance where the models that we consider do fit reasonably well, that would, number one, warrant further investigation, but it would make me think my idea and the motivation for it is not that far off. So we do this plenty of times, and we see that there are cases for the powered Lindley, for the science skewed von Mises, where those models will outperform the others. Of course, maybe it is a bit biased because we do it many times, and inherently, or inevitably rather, it will occur that they will be better. But in this case, I have to go back and I have to think, did it fit the best? No. There is no one ring to rule them off, but it depends on the data. So when I go back to my idea of the bootstrap as an illustrative exercise, it's not to force the idea of the powered Lindley, but it is to show at the end of the day, if the caribou data by pure chance was good enough with the powered Lindley, we would have seen it. We would not have given it an extra thought further. However, this systematic consideration of these specific candidates gives insight to how alternate models respond, at least in this animal movement setting. And then the additional insight gained by the bootstrap exercise shows that these models are reasonable candidates that should be considered in future within this realm. I say they published work, not quite published, but our paper is under review. Epilogue of my story, and then I'm wrapping up. Inspiration for new ventures in our research world, they come from various sources. I think about skewness, and I think about mixtures, and I think about animal movement, and what type of theoretical pinpoints are there that sometimes can kind of restrict the model, and then we can make these little adaptations in order to reach a meaningful contribution. Did our developed models exclusively emerge victorious in our 3 stories? Absolutely not. But that's not the point I'm trying to make. The point I'm trying to make is the systematic construction and approach in these 3 stories and elsewhere yields insight and particular intellectual return on the intricacies of these theoretical underpinnings and shows a competitive edge. Sustained relevance? Why are we keep on doing this? At the end of the day, this is not a hunt for the Holy Grail. No one ring to rule them all. But it is rather a continued journey of theoretical interest, at least for me. And it's great that it is incorporating this applied impact when we're looking at economic data estimation, we're looking at count data estimation, we're looking at animal movement modeling, because our inspiration are drawn from the practical environment. It will inevitably, in some way, have a resulting or inherited practical impact. And our focus point, our focal point, remains in the theoretical description and systematic construction of models that can depart from previous type of restrictions considered. Thank you to the CoE, not only for this invitation, but the astounding support that you offer across South Africa for mathematical and statistical sciences. Of course, I want to thank my colleagues. I'm thinking immediately of Kopika, I'm thinking of Anita, I'm thinking of Anay, I'm thinking of Professor Bakker herself. I'm also thinking of the rest of my team that's still working with me. I'm thinking of Paul, I'm thinking of Arnu, and thank you, and the lead, and there's just a whole bunch of, oh, I feel like I'm at the Oscars. Just want to thank everybody. And I have a little bit of references, but if anybody feels keen on wanting to dream a little bit about this further, or you want to discuss something about this a little bit further, please feel free to contact me. Thank you so much.
Thank you, Professor Ferreira, for your interesting stories today. It was really nice, and we hope that there will be a continuation, a next chapter of stories for us in the near future. And we are now inviting the audience for any questions or comments. Let us first focus on the Zoom audience. Yes, there's a hand. David, please go ahead and ask a question.
Just a short thing. Can I see the PMF for the multinomial on, I think it was equation number 3?
Yes.
You can go ahead, David.
It's just missing a factorial. Okay, thanks.
Oh, okay, yeah.
It's missing a factorial in the denominator there.
Thanks a lot, David. I think we need you for editing it next time. Thanks a lot, David.
Sorry, apologies. Yeah.
Keep in touch. Keep in touch. Anyone else? Okay, there's from Hopika a comment. She's thanks for the excellent, giving us the best possible Reader's Digest. Thanks, Hopika. I agree with you. Anyone else? In the meantime, Johan, while we're waiting for other questions, can I ask you what would be your next storylines?
Yeah, the next storylines. I think I had a discussion this morning. I'm not going to give you a direct answer, but I'm going to give you an answer. I think the very valuable thing here is that we all need time to think. And when we are going to work in our environment, or we're working in entropy, or we are working in animal movement, the most valuable unit of currency for me at this point in my life is thinking time and reading time. And I think we all sometimes feel so pressured to write, and we feel so pressured to publish, and we feel so pressured to teach, and we must supervise, and we must do all these things that I boil it down to a lot of thinking. We must think more, because if I don't think, I cannot do. And if I don't do, I cannot write. If I do not write, I cannot publish. So it all boils down to thinking. And the reason why I'm saying that as my response is that the inspiration for these stories come from practical environments. Animal movement can be multimodal, maybe it can be skewed. We think about inner type of processes where equidispersion is a real challenge, theoretically imposed on practical environments. So the reading and thinking about a next type of story is essential to think, where are we going next? Currently, my next type of story is built around particular and curious type of mixtures, but some of that work needs a bit more thinking. But hopefully I can visit the CoE again and share some ideas in the future.
I'm looking forward, and I think all of us are looking forward. And I think it's also good advice for our youngsters. I think there are youngsters among us. Is the time under the tree. I always refer to it as sit under the tree and think, and read your stuff and think, because as today is so much pressurized, and I think that is well a good advice from your side as a young academic for the other youngsters to follow. Any other questions? Diane, anything from the audience there?
Nothing from our side. Thanks, Andrea.
Okay, thanks, and then I hand it over to you. And thank you again, Johan. And from my side, let us give him applause. I think it was really interesting for all of us. Thanks, Johan. Thanks to CoE.